Great. It's really a pleasure to be here at this workshop. I, in general, really love events that combine math, computer science, and scientific applications. I'm going to be talking about how we can now say goodbye to equivariance constraints. It doesn't mean we have to say goodbye to the research on equivariances. We can use that in various ways to build models that expand beyond these constraints, but still have really useful inductive biases. I'll also be saying goodbye to constraints in general, but equivariances will be kind of a running example that will help us understand what I mean. This is also work that's been done in collaboration with a number of people and has been influenced by discussions with many people, and so I'd like to thank them here as well. Okay, so I'm going to start with a question that I ask in virtually every talk I give, regardless of what the talk is about. So don't worry if you've seen this before. The talk is about something different. But the question itself is still going to be relevant. So let's suppose we're modeling these airline passenger numbers recorded monthly. And we'd like to make predictions up until, say, 1961, and we're going to consider 3 different possible models that could fit these data and help us make our predictions. Now, you might not like any of these models, but suppose you have to choose one of them. I'm going to take a vote. Who's going to go with the linear function? Raise your hand.
I have to know what n is.
What n is?
Sample size.
OK, let's say it's a couple hundred.
Okay, thank you.
The cubic function? OK, the 10,000th order polynomial. OK, so I'm hoping by the end of the talk we'll all be going with choice 3, but we'll still be a little bit unhappy about it because it doesn't have enough parameters, right? And in practice, we're actually already implicitly making this choice very often. So it's not uncommon to use neural nets with tens of millions of parameters to fit problems with tens of thousands of data points to make this concrete, to go back even just a few years. If we're considering a problem like CFAR10 that has 50,000 training points, it's very common to use a ResNet on those problems that has about 10 million parameters. But even if we're not working with neural nets, let's say we're more classical statisticians and we like models like Gaussian processes, we're working already with models that are like an infinite order polynomial. If we're using a Gaussian process with an RBF covariance function, we can actually derive the model in this dual space, thinking in terms of parameters instead of functions, and we have an infinite number of parameters, and it's not just some sort of mathematical sleight of hand. These models are meaningfully very expressive, more expressive than any possible neural network that we could fit in memory. And in fact, some of these covariance functions for Gaussian processes were derived by taking infinite limits of neural networks. And so we're already making this choice, and we see that it works well in practice, but why does it make sense as a modeling decision? Like, I'm assuming if you didn't make choice 3 here, you were worried about overfitting in some way. OK, so we'll be discussing that throughout the talk. But before we get to that, I'd like to ask you a different question. And in general, I'm going to ask lots of questions. So don't be shy. Just answer. And feel free to ask me questions as well if you like. I'd like to make this interactive. Can you tell me something that makes deep learning different from other model classes? Nothing. Well, I agree with that answer, but I mean, well, actually, I don't fully agree. I mean, there are a lot of things that don't that we think do, but there are some things that are different. And any thoughts?
You want an example of something?
Sure.
I would say, as a dinosaur statistician, that when I do my optimization, I think I'm getting the solution, and deep learning works by the optimization providing some regularization.
Mm-hmm.
And so the models, what we mean by the model in classical statistics, I don't include a regularization term due to the optimization itself.
Right. So the implicit regularization of the optimization procedure might be more important when we're learning a neural network model than if we're working with a different model class.
It's certainly more important than when I do least squares.
Right.
Yeah.
Yeah. OK. It's a good example. Anything else?
It's faster.
It's faster.
Yeah.
How so?
Squares?
No, not in least squares, but at least from my experience, it's like you said, Gaussian processes, fitting them, fine-tuning, playing with the kernels, takes forever. Deep learning, you just shove it in 3 minutes later, you get a good solution.
Interesting. Okay, so we'll come back to that. So I'll talk about what I think is actually sort of different as well. These are things that I don't think are different, but many people do often use as examples for how neural nets are distinguished from other model classes. So we've sort of touched on one of these already in the first slide, overparameterization, just having many, many parameters, often more parameters than data points. As I've mentioned, this, of course, is not distinct to neural nets. Gaussian processes provide one of many other types of examples of this, but we often associate it with deep learning. There's also this phenomenon called benign overfitting, the ability to fit a mix of signal and noise perfectly with no training error, but still provide reasonable generalization, as we'll discuss, also not distinct to deep learning. Another one is double descent. Interestingly, the paper that popularized double descent about 8 years ago or so did have examples outside of neural nets, but it's often still very specifically associated with deep learning. And we can understand really how to resolve these phenomena through this perspective that is really encapsulated by the title of this talk. Like, we don't want hard constraints. We really want to embrace a flexible hypothesis space, but in combination with soft rather than hard inductive biases, so that we prefer certain types of solutions over others, even if they fit the data equally well. And so this is a principle we can apply in deep learning, but also really for virtually any other model class, and it also applies to equivariance constraints, which we'll be discussing in a bit more detail in a moment. So we typically think of generalization, inductive biases in terms of restriction biases. So if we go back to that first example, using a model with fewer parameters, it's constrained in some way. Like, if you use the linear function to fit that airline passenger data, you're not going to do something horrific, right? Like, you're not going to get some really wiggly line that's just going to provide crazy nonsense predictions outside of the data. So you're safe in some sense because you've constrained the size of your hypothesis space. There are many other examples of this in deep learning. Convolutional neural nets could be a good example. So we remove a lot of parameters and we enforce parameter sharing. That's another sort of hard constraint. It leads to approximate translation equivariance, et cetera. This is often a principle that we try to account for when we think about model construction. But we don't have to really use restriction biases. We can often embrace a really flexible hypothesis space as long as we have these so-called soft inductive biases that will guide us to structure where it exists without, as we'll see, really penalizing us very much if it doesn't. So in this conceptualization here, we have restriction biases where we're not supporting very many different types of solutions, and then we're relaxing them into softer inductive biases where we expand the size of the hypothesis space, and the different colors represent our preferences for different types of solutions. So in the picture on the left, we basically have a uniform bias. In the picture on the right, we have these softer biases, but in darker blue, we have stronger preferences for those types of solutions. Okay, so let's go back to the polynomial example. Let's suppose we have a polynomial of order j, and we can make capital J very large. And let's also suppose that we regularize this polynomial so that we're penalizing the higher order coefficients more than the lower order coefficients. There are many ways that we can do this, but basically we're penalizing the norm of each coefficient in a way that increases with the order of that coefficient. So I've given an example here. We just raise it to the power of 2j. And what that means is that if we have a data fit term, which we really prioritize in some sense, so we pay a significant penalty for not fitting the data perfectly, but we combine it with this kind of regularizer, the model will be very expressive. If we have a large j, it'll be capable of fitting quite a variety of different functions, but it will also have this Occam's razor bias. Like, given that there are many different settings of parameters, if we have a really high order polynomial that can fit the data perfectly, it'll prefer the setting of parameters that really relies more on the lower order coefficients. And so if you can fit simple structured looking data with basically a straight line, this model will fit it with a straight line. If you increase the complexity of the data, it will adapt its complexity accordingly. So here we have that order dependent regularization in blue. We have an unregularized high order polynomial in brown. This is a 150th order polynomial. Here we have 5 data points. And so already we're seeing, okay, we went with this high order polynomial on a problem that's kind of analogous to that airline passenger problem, and we're not seeing overfitting. We're seeing fairly reasonable behavior, and we're seeing this natural adaptation of complexity as the data itself becomes more complex. Okay, so let's consider another philosophical question/interlude. Do you think we should use a different model depending on how many training data points happen to be available. So when I asked that first question, actually, an audience member asked, how many data points do we have? So let's take another vote. Raise your hand if you think we should use a different model if we have, say, 5 training points versus 5 million data points. Raise your hand if you think we shouldn't use a different model if we have 5 data points versus 5 million data points. Leaving computation aside.
And how about interpretation? That is, you haven't said the exploitation task. Like.
OK, so right now I'm thinking mostly about performance.
Okay.
We can talk about interpretation as well, but yeah.
So I vote.
The second one or the first?
For different sizes, for different sample sizes, different models. For
different models for
so
we
I'm
might
trying
want
to do subsequent inference.
OK.
So maybe I would change my mind, especially since I know what your answer is.
Right. OK. Yeah. So everyone's learning. That's good. Well, let's think about this philosophically. So what do we actually believe? So basically everything I'm going to say in this talk, and ever probably in my life, is that we should just honestly represent our beliefs in what we're doing. And do we believe that the data generating process is more complicated or sophisticated in some way if we happen to have access to more data points? Probably not. If we have 5 million versus 5 data points, it probably doesn't tell us anything about our beliefs about the underlying ground truth that generated that data. It might in some very special idiosyncratic settings, but typically it wouldn't. And so we should just honestly represent our beliefs. If we think that the real world is a complicated place, and it often is, it often has some nuance associated with it, we should really embrace that belief and reflect it in the way that we construct our models. And that usually means embracing an expressive hypothesis space. So I would say, in principle, the answer is no. As a quick aside, and we don't really have time for asides, but oh well. In Radford Neal's PhD thesis, he had this kind of beautiful excerpt somewhere in the beginning where he says something like, whenever we have a simple model that performs well, we can always build a more complicated model around that has whatever properties cause the simple model to perform well that will perform even better. And he sort of exemplifies this by saying, well, if we're doing handwritten character recognition, there'll be like strange writing styles or weird ink blots. There's just something else that we can account for and kind of enlarging the expressiveness of our model class that will lead to better performance. OK, so let's go back to the polynomial example. Let's consider a high-order polynomial with the order-dependent regularization in green, a high-order polynomial without regularization in purple, and a small polynomial, degree 2, in blue. So for a variety of different data sets, across sample sizes, the order-dependent polynomial has the best performance, or it's comparable to the best performance. So if we have data generated by a second-degree polynomial, of course, the degree 2 polynomial will generalize well on that data, but so does this high-order polynomial with the order-dependent regularization, and it learns at about the same rate in this case. If we have data generated by a 15th degree polynomial, we can see that the order-dependent regularization works significantly better than the unregularized 15-degree polynomial, and the second-order polynomial quickly saturates in what it's able to learn from the data after only seeing a small number of data points. If we have data that's generated sort of out of distribution in some sense, we again see that the order-dependent polynomial is better than all the other models for any sample size, but it's also good at any sort of number of training data points. And so this is because it is encapsulating this philosophy of embracing flexibility combined with this soft Occam's razor bias. So if it can fit the data with a straight line function, it will use the straight line function, even though it's capable of representing many other functions. OK, let's start talking about equivariances now. So I briefly mentioned convolutional neural nets are another famous example of embracing hard constraints as an inductive bias. And it's very sensible, and just like with equivariances in general, that doesn't mean we should just throw away conv-nets, but we can actually use their biases as a soft bias in a more expressive model class. So one way that we can derive a convolutional layer is by starting with a fully connected layer, removing a bunch of parameters, and then enforcing parameter sharing. So the purple lines here correspond to parameters that have the same value. The green lines have the same value as well. If we instead wanted to relax this hard architectural constraint and make it a soft inductive bias, a very simple sort of naive thing we could do is go back to the fully connected neural net, introduce a regularizer that penalizes the norms of any parameters that don't exist in a conv-net, as well as the distances between any parameters that otherwise would have been shared in a conv-net. And so the extent of this penalty will control how much or little this model actually behaves like a convnet, but it will expand its expressiveness. And just incidentally, the lack of, the parameter sharing and the sparsity correspond to translation equivariance and locality assumptions. And so we wouldn't necessarily exactly believe these assumptions, even in image recognition problems. We don't necessarily want exact translation equivariance. We don't necessarily want locality. In some sense, we should be responsive to the data if it's telling us that there's something that we've missed. A more elegant way to relax these types of hard equivariance constraints into softer equivariance constraints is through some work we did called residual pathway priors. So here what we can do is we can put a distribution over the parameters of the neural net that has a covariance matrix that lives in this equivariance subspace of our choice. And this is generated from some other work we did called the equivariant MLP. It's sort of a very flexible way of sort of constructing different types of equivariance constraints, plus some orthogonal complement, PP transpose. And so that sigma b kind of controls how much we want to relax this constraint. And this is part of a broader kind of conceptual framework where we can imagine models that have some sort of restrictive layer, and they try to explain as much of the data as we can, and then whatever is kind of left over, we explain, like the residual, we explain with this flexible layer that has weaker inductive biases. And so you could map this back onto this running polynomial example. We have the high order polynomial with this order-dependent regularization. It will try to fit as much of the data as it can with the lower order terms. Whatever is left over, it fits with the rest of the model. Okay, so one thing we found that was a bit surprising to me at the time, but not really anymore with hindsight, is that this residual pathway prior idea would often work as well as the exact constraints, even when the constraints were perfectly specified. So we're modeling molecules that we know are rotation equivariant, but now we're just saying, oh, we have like approximate rotation equivariance and maybe a bias towards that, but we can have other solutions. The RPP will work just as well, sometimes even better. Another thing we found is that the details of this regularization, so the values of sigma b and sigma a, for example, weren't that important. So all we typically needed was a very, very soft bias towards these types of constraints, these types of salient structures we might think could describe the data to some extent, and we would often be competitive with perfectly constrained models. If there was some sort of approximate symmetry, so let's say we're modeling some dynamical system and some conservation law isn't entirely preserved, there might be like a pendulum, but there's wind in the air, there might be a problem where there's sort of like reinforcement learning, you have friction in contacts and so on, you would do much, much better with this approach. And if you had some sort of misspecified symmetry, so let's suppose we specify our equivariant subspace to be like a larger group than the one that would be like the perfect description of the data, we would also see that it would collapse down very quickly onto sort of the right description of the problem. It would be very competitive, often the best of these three alternatives. So EMLP represents hard constraints. MLP is basically an unconstrained model. The RPP are these soft constraints. We looked at these, as I mentioned, constraints in reinforcement learning settings where there are various symmetries and approximate symmetries. So as I mentioned, you can have subtle effects like rewards moving in one direction or perturbations like wind or minor tilt angles and things like this that somewhat break sort of symmetries in these problems. And this is actually very suitable to this type of residual pathway prior approach. By using these kinds of larger groups in the equivariant subspace, we were able to see big improvements in performance over like standard soft actor critic models for controlling problems in Mujoko in this case, in a model-free setting. We also looked at this when we were thinking about transition models in model-based RL, especially for longer kind of rollouts, and found that this residual pathway prior approach was quite a bit better than either hard constraints or no constraints. We had another approach to trying to learn invariances where we're basically trying to learn distributions over data augmentations that could describe certain constraints. Like the idea there was like, we believe there's some exact constraint in the problem we're modeling, but we don't know exactly what it is, and so we would like to just discover it from the data. And I think this is an interesting learning question in itself, because our standard training objectives don't select for constraints. Like a more flexible model will be able to fit the data more closely, and so quite often they're not sort of incentivized to find constraints, and regularization can provide this incentive, but it won't necessarily provide an incentive for the right constraints. Like let's say you have, like just as a toy example, some digit classification problem. Like a 6 is rotationally invariant until it becomes a 9. So you have like a certain amount of rotation invariance. You want to learn exactly what rotation invariance sort of describes your problem. So we developed this approach that would enable people to do this. And again, we found in a bunch of QM9 and other problems that it was fairly competitive with just using the constraints that we knew to be true for those problems. Okay, so you might be wondering, well, aren't convolutional layers, for example, much more efficient than MLP layers? Like, it's not just about inductive biases and philosophy. We have to care about computation and practical considerations. And I think in some instances, this is absolutely true. So if we had some like standard image classification problem, and we had a 1,000 by 1,000 pixel image, and then we had maybe like 1,000 hidden units in an MLP, we already have like 1 billion parameters, right? And not even a very interesting model. Like with that same computational budget, we could probably build a much deeper convolutional neural network that would have just properties that would be much more suitable for that kind of problem. So in some instances, that is true. Like in practice, you have to try to understand how you can best use the computation available to you. I still think in most cases that involves soft rather than hard constraints, however, and this is something that we studied actually very carefully when we were trying to understand whether we could systematize this process of replacing dense linear layers with structured matrices. Like what sorts of assumptions are we going to want to make towards better compute optimal scaling? So you may have heard of these chinchilla scaling laws that tell us that quite often, if you're able to vary the size of your data set as well as the size of your model, often performance follows some sort of power law. And the idea was maybe we can sort of make certain design decisions in our model that will change the exponents of these power laws. And if we could do that, that would be very exciting, because it would mean with increases in computation, we would see exponential improvements in performance. And so I don't have time to give the full talk about that work, but basically what we did was we developed this Einsum formulation that encompassed many different types of matrix structures that people know to work well, like convolutional structures, Toeplitz matrices, tensor trains, monarch structures, et cetera. And we could control this with very interpretable parameters that would specify things like the extent of parameter sharing, the rank of the matrices, the speed of the multiplies, et cetera. And what we wanted to do is really just kind of understand the science of scaling. Like what sorts of principles should we be embracing towards the best compute optimal scaling? And here omega shows the extent of parameter sharing. So 0 is no parameter sharing, 1 is like a lot of parameter sharing. And what we found is actually parameter sharing was a very bad principle for compute optimal scaling. So the structures that did not have parameter sharing had much better scaling exponents. Okay, so conceptually, we've been talking a lot about soft inductive biases. Here we have an illustration of how those biases might affect the optimization trajectory. So in the left panel, we have an example of a very flexible hypothesis space, but a uniform bias. So no particular preference for one solution over another if we're not counting a fit to the data. And so indeed, quite often in these instances, we will see some sort of overfitting. In the middle panel, we have an expressive hypothesis space, but with stronger preferences for certain solutions over others in darker green. And so in this case, we might often achieve good generalization. In the right panel, we have restriction biases where we're choosing something like analogous to the linear function or whatever that's very constrained, it's kind of safe, it's probably not going to overfit, but it's also not going to give us really great generalization. Okay, so this is all intuition, and we see that empirically we are getting results that align with this intuition, but can we actually formalize this a bit more rigorously? And the answer is yes. And interestingly, this isn't very well known. So while I think frameworks for generalization bounds like PAC-Bayes have a lot of name recognition, there are a lot of misunderstandings about them. For instance, one common misunderstanding is that PAC-Bayes generalization bounds only apply to models that have distributions over parameters, which are not the models we're typically training, especially in deep learning. That's just not true. We also can derive much simpler bounds, basically a finite hypothesis bound with a prior. And this shows up in textbooks, even like the Ben David Shalev Short's learning theory textbook, which are saying nothing about distributions over parameters or anything like that. They're sort of simplifications of Pac-Bayes in some sense. They're very easy to derive. It's just a combination of Hofting inequality and a union bound, and we arrive at the bound in equation 2. And so let's actually make sure we understand this. So what it's saying is that expected risk is upper bounded by empirical risk, our training loss, plus this complexity penalty term. So let's break that down. So the delta here just corresponds to our confidence in the bound. So if we are trying to make a stronger probabilistic statement, we have smaller delta that loosens the bound. N is the number of points we're using for the empirical risk, the number of training data points. This log 1 over pH is some log 1 over some prior density. Now, importantly, this prior is not the prior that is used by the model, implicitly or explicitly. It's just a weighting function that we choose to evaluate the bound. And so if we choose a prior that has low density under the types of solutions the model is finding, it will just provide a very loose bound, and it won't be a good description of how that model is working. And so, again, I'll sort of emphasize this. Like, if we choose something like some Gaussian prior or whatever, it's not saying that, like, oh, this only applies if the model is using that prior, or if that prior is, like, well specified in some way, or was used to generate the hypothesis that describes the data. It's just something we can choose, and if it's a bad prior for describing that model, we'll have a loose bound. Okay, so one prior I found to be very useful in evaluating these bounds is called the Solomonov prior. And so it's equal to 2 to the negative power of Kolmogorov complexity divided by a normalization constant. Based on Kraft's inequality, the numerator will be less than or equal to 1, so the normalizing constant will be less than or equal to 1, which is nice for plugging this into a bound because we get like another upper bound in equation 3. And then we can upper bound this prefix-free Kolmogorov complexity, which is the shortest program that can basically output this hypothesis in bits by the stored file size of the model, and then we can go ahead and evaluate this bound. And so actually evaluating these bounds is very simple. All you do is train whatever model you wanted to use with whatever regularizer, optimization procedure, et cetera. You evaluate the training loss for whatever solution you find, H star. You evaluate this upper bound on the Kolmogorov complexity based on the stored file size of the model, and then you evaluate the bound. And this also leads us to a prescription. So in order to have good upper bounds on generalization performance, what equation 3 is saying is we actually do want an expressive hypothesis space because that's going to enable us to fit the data really well and have low empirical risk. And we want a compression bias. Do you have a question? Yep.
Yeah, just a clarification. So this bound is uniform over all the H's?
No. So it's basically saying that compressible H's have exponentially more weight. So the standard finite hypothesis bound would be like a uniform prior over H.
But in some sense, I guess my question is whether you want to have some guarantee that it's also worked after you do the empirical risk minimization, right? So you are free to move H.
I couldn't hear your question.
Sorry. So I guess my confusion, maybe this is confusion notation, but you want to adapt H to the data, right? So you need to be able to make statements that hold for many, many H's at the same time.
Yes. So that's where the union bound comes in proving this. This
is where you have. This is the reason why you have the first term in the square root, right?
I mean, I'm not sure why. Like, I'm not sure if that's why we have a square root. But this bound does hold for any H that you use. Yeah. You basically in the proof. So I actually included it. Just kind of, it's a single sort of column in the appendix. It's not original in the sense that this result is I think known historically. But basically you just have sort of this initial sort of assumption of independence in your risk, which allows you to use Hofting's inequality, and then you do a union bound so that it applies to any H in your hypothesis space. Okay, so I mean, one sort of detail that might be worth mentioning is you can get tighter bounds, of course, if you like then try to compress your model more. And then there's this question about whether the compressed model is a good representation of the original model. Quite often it is, and quite often you don't actually need to do that anymore, but I can talk about that a bit more offline. So here we have a visualization of this trade-off between the empirical risk and the compression term. So if you can kind of achieve good compression and retain low empirical risk, you'll get your best bounds, and these bounds actually apply to very large models, even LLMs with billions of parameters. And quite often, they get better as you increase the number of parameters. And this is partly because the larger models tend to find solutions that are actually more compressible. So I said like a recipe for model construction involves expressiveness combined with some sort of compressibility bias. It turns out that scale seems to provide an implicit bias for compressibility. And that actually explains a lot of why larger models tend to work better. It's actually not because they're more expressive, it's because they find solutions that are more compressible. Okay, so just quick note on pack Bayes. So you basically replace this log 1 over pH term with a KL divergence between a posterior and a prior. And the reason for that is if you don't care precisely about what your solution is, it's just sampled from some distribution of good solutions Q, then you can get some bits back and get a tighter bound. The criticism of that is quite often we're not using models with distributions over parameters. I don't know. I mean, I think it's useful to sort of understand the connection between these things, especially because this thing called the marginal likelihood, the Bayesian evidence, is actually directly corresponding to a pack Bayes bound. And this is something that we know how to compute very well in many instances. So quickly return to this benign overfitting example. So we've had this high over polynomial with this order-dependent regularization. We can throw just complete uncorrelated noise at it, and it can still fit it perfectly. And so this like benign overfitting, I think first surfaced in the Understanding Deep Learning Requires Rethinking Generalization paper from 2016. They showed that a convnet could perfectly fit images with noisy labels, but of course generalize well when they're trained on structured image recognition problems. This was described as being in the face of everything we know about generalization because like Rademacher complexity and VC dimension and so on basically measure the ability for a model to fit noise. That's not what these bounds, pack Bayes, countable hypothesis bounds of the prior, et cetera, are measuring. Instead, you can have an arbitrarily flexible hypothesis space, but you can still have good generalization if you have this compression bias. We can exactly reproduce this kind of behavior with a polynomial, and a polynomial is about as simple as it gets. So if understanding deep learning requires rethinking generalization, then so does understanding this basic polynomial. We also can exactly reproduce the experiments in this paper, the CFAR experiments with Gaussian processes. So GPs basically assign a flexible distribution over functions. In panel A, I'm drawing from that prior over functions. Panel B, we see a posterior predictive distribution, fairly reasonable. In panel C, we have a bunch of corruptions. So we have a mix of noisy and structured data. We can still fit the data absolutely perfectly with the GP. The GP doesn't really want to fit this data perfectly, but if you tell it, okay, you have to, in our Gaussian likelihood or whatever, we don't have much label noise, it's able to do it. And you can actually precisely quantify how much the GP or any model really wants to fit this kind of data through this thing I mentioned called the marginal likelihood. So the marginal likelihood is precisely the probability that will generate the data if we're sampling from the prior. So if we go back to panel A, we'd have to sit there sampling functions for a very, very long time to get anything that looks like this red curve. It has very, very low prior density in this distribution over functions. But it does have non-zero probability. And so if it sees that data and you tell it you have to fit that data, it's like, okay, I don't want to do this, but I can do it. And I can reproduce benign overfitting. We can also use GPs on those CFAR image classification problems and show that as you vary the number of altered labels, it can provide a perfect fit to the data, but still sensible generalization. And the marginal likelihood of the GP continues to go down as you increase the number of altered labels. Again, reflecting this idea like, I don't want to do this, but you're making me do it. You can do exactly the same with a neural network. And this corresponds to these pack Bayes generalization bounds.
Sorry, just to be clear, as you're forcing it to fit to corrupted labels, it does generalize less well as measured by the marginal likelihood? Is that?
So the test error gets worse as you increase the number of corrupted labels, which is true in the Rethinking Generalization paper as well. Mm-hmm. The marginal likelihood also gets worse. So it's saying, okay, it's less likely that we're going to generate this data under our distribution over solutions in the prior. For the mixture of them, yeah. And so the marginal likelihood gets increasingly worse as you increase the number of corrupted labels. So it's most happy when it's only structured data at the left point of this curve, and then it gets increasingly less happy as you increase the number of corruptions. OK, so finally, what really makes deep learning different? One thing that I think makes deep learning somewhat distinctive, not completely unique, is its generality. So it seems like we're able to use neural networks to solve quite a strikingly large variety of different problems. And that isn't typically true of many other model classes. And it sort of stands contrary to ideas around things like no free lunch theorems. So there are many no free lunch theorems. One of the most well-known ones says every learner is equally good in expectation over all data sets sampled uniformly from a distribution over data. There are others like no single learner can achieve high accuracy on every problem. And this sort of leads to a prescription that like we do want tailored inductive biases, even restriction biases. This idea that like we want to understand the problem that we're modeling really well and all of its idiosyncrasies, and we want to bake that knowledge into our model architecture, because if our model is doing well on one problem, the no free lunch theorem implies it's going to have to be doing poorly on other problems. However, in practice, we've seen exactly the opposite. So we've seen a confluence of more specialized models towards more general purpose approaches. So feature engineering towards architectures that are domain specific, like CNNs for vision, recurrent nets for sequences, MLPs for tabular data, regression, et cetera, to basically transformers for everything. Well, how is this possible? It's possible because the real world is a small corner of all possible data sets. It does contain a lot of structure. And our contention is that the distribution over real world problems has a bias towards low Kolmogorov complexity, and so do many of the models that we're constructing. And that bias seems to increase with scale. And this, as we've discussed, provably provides sort of a recipe for good generalization, if it's true, over quite a wide variety of different problems. And so we're seeing, for instance, that if we just use text-based pre-trained language models, we can get good zero-shot forecasts on problems like time series. So this is without any domain-specific fine-tuning. You might wonder how is that possible? They don't seem like very similar problems. It's possible because the text-based pre-training, in some sense, instills certain biases into the model that are going to be generally applicable, like a compression bias, a sort of Occam's razor bias. We saw this more strikingly in materials generation. So here we're looking at text-based pre-trained models like Llama 2 or whatever that's been trained on next word prediction. In this case, we fine-tune it on atomistic data represented as text for generating crystals. And we found that that combination of text-based pre-training plus fine-tuning worked much better than just like domain-specific training. And part of the reason is that text-based pre-training actually helped the model discover things like rotational symmetries and so on, which were actually good descriptions of the problem. And so like one way of discovering an equivariance is to have a compression bias. And this means that you can, like, even if you have very different problems, like maybe one problem is rotation equivariant molecules, another is like translation equivariant images, et cetera, even though normally the features associated with being able to solve those problems well would look very different, if you have a model with a strong compression bias, it might be able to discover that salient symmetry in each case. All right, so in short, time to say goodbye to hard constraints, but not goodbye to all of the great work that's been done on understanding how we can encode certain hard constraints in our models. We can just relax them into broader, softer inductive biases. This perspective really helps us understand, both intuitively and formally, a number of generalization phenomena in deep learning and beyond. Residual pathway priors are one way to exemplify this prescription for model construction. I think even if we're thinking about like computation and practicality, et cetera, this is often a preferred sort of approach, as we saw when we were looking at scaling law behavior. But I think there is still a lot of work to be done on how we can exploit that structure in some sort of subspace, et cetera, for more scalable computation. Final slide, I'm going to ask this question again. So are we going to use the linear function to fit the data? Raise your hand. Cubic polynomial, raise your hand. OK. 10,000th order polynomial, raise your hand. OK, changed a few months. Good. OK, thank you.
All right, due to time constraint, we're going to take one question. Is there any burning questions? Yes, please.
Thank you for the talk. So I was wondering, so you said computation aside, yeah, of course, we're going to go with the more complex model because we can like learn better things, like be more generalizable and stuff. But anywhere in this work do you think about explainability? Because, so for example, when you present this slide to someone and you say, I went with the third model, then the explainability would be really tough. But if you go with the first one, although you may be losing in terms of accuracy, but it's easier to explain the model to a person. Or for example, in the CNN case, it's easy to look at the trained filters and see kind of what the model is doing, but with an MLP, it's probably catching some more intricate symmetry for us to understand, but I mean, we lose on that.
But yeah, so I hear your question. So the question is like, do we lose something else by embracing expressiveness, like explainability? I think the answer is no, in the sense that like we have to be very careful if we're constraining our model because we want it to be more understandable. Maybe it's more interpretable in some sense, but the interpretation is wrong because the model is not reflecting our honest beliefs. And so that can be dangerous in itself. Secondly, I think the most exciting thing about doing AI for science is really about discovering things that we didn't know before. And so there's this approach where either we just like try to encode all our scientific knowledge very carefully into our model and then just sort of run the algorithm and have it make predictions. And maybe that's useful for a particular application, but it doesn't help us to develop new scientific insights into the problem that might generalize to other problems. And so I think we can possibly get that through expressiveness, basically having the model discover things that we didn't already know, and then doing the very hard work in some cases to try to interpret it. Like maybe there's just no way around that, but I think it's worth it, and it's more of an honest reflection of our beliefs. I think also, in terms of these bounds and thinking about expressiveness, et cetera, I probably should say, I don't think the most interesting thing about generalization bounds are the numerical guarantees on performance. I think those are honestly almost meaningless. Not meaningless, but close to it, because you have distribution shifts and other things like that in the real world. These bounds become interesting when they give you some insight into why the model generalizes. And so if you, for example, can understand that when you use certain priors for evaluating the bounds, like a Solomon prior, and they have high density for the types of solutions the neural networks are discovering, then that tells us, okay, well, the neural nets are maybe doing something like approximating Solomon induction. And if we can come up with a better prior that more closely describes these models, we'll get tighter bounds, and that helps us kind of better understand these models. So if the bound says something like, okay, the model is working well because it's finding a good way to compress the data, and it actually is able to do that even better when you make the model bigger, that's really interesting, and it does tell us something about how to develop effective learning systems. And so from this perspective also, I like to sort of embrace flexibility.